Hey everyone, today we're going to show a trig identity, namely that the left-hand side of sine 3 theta is in the end equivalent to the right-hand side of 3 sine theta minus 4 sine cubed theta. So this is one of the more difficult identities that I've done with my class. Let's try it out. Also, we get to choose, as always, which side we want to work with, which side we want to leave all on its own. Because I've thought about this before, I'm going to choose to work with this left-hand side, simply because it's going to be really hard to work with the right-hand side, where we have regular sine thetas and have sine 3 thetas emerge out of it. That's, for me, going to be very difficult to do. But I think it'll be straightforward enough to get the left-hand side to go down into regular sine thetas. Because sine 3 theta can be written as sine of theta plus 2 theta. We can break apart that compound angle, and then we can use our compound angle identities, which we've looked at a few times before. So if we have it as sine of theta plus 2 theta, that's like a plus b, right? Sine of something plus something. We have a compound angle identity. That means we can write this as sine of the first part times the cosine of the second part plus the cosine of the first part times the sine of the second part, like so. That's one of our compound angle identities for sine of a plus b. Now our goal is, again, to go from here all the way to the right-hand side, leaving the right-hand side untouched. So let's go ahead and do that. First, we have sine of theta times cos of 2 theta. Sine of theta is what we want in the end, so that is great. We'll leave it as sine theta. Cos 2 theta, we have a few identities to choose from, right? Now, we want all sine thetas in the end. So, out of the potential for convenience, let's say, let's use the version of cos 2 theta that introduces sine squared thetas, right? And that one is 1 minus 2 sine squared theta. That is one of our double angle identities. Let me just double check that that's true. Yep, that is true. And so we can apply those double angle identities within our compound angle identity. And then in the second term, cos theta times sine 2 theta, we have a nice double angle identity for that one as well. That one has to be 2 sine theta cos theta. Okay? So now let's multiply through what we have. The sine theta is going to multiply through these brackets, and we'll combine the cos thetas in the second term. So we'll have sine of theta minus 2 sine cubed theta. That seems encouraging. Plus 2 sine theta cos theta times cos theta gives us a cos squared theta term. So now we have a sine theta, we have a 2 sine cubed theta, and we have a 2 sine theta cos squared theta. Now, the only part of this expression that is not sine is this cos squared, and luckily, this might ring a bell for you. We know that through our very first Pythagorean identity, the fact that sine squared theta plus cos squared theta is 1, if we rearrange that one, we get that cos squared theta is equal to 1 minus sine squared theta. And so we can make a substitution, right? And so now we're going to have sine theta minus 2 sine cubed theta plus 2 sine theta times, whoopsies, theta, times in brackets, replace the cos squared with 1 minus sine squared theta, like so, right? And then this is going to start to take shape. We'll have sine theta minus 2 sine cubed theta plus 2 sine theta minus 2 sine cubed theta, right? Once we've expanded that properly. And now you guys can see we're just about done. Sine theta plus 2 sine theta leaves us with 3 sine theta. And minus 2 sine cubed minus 2 sine cubed theta is minus 4 sine cubed theta. And that's exactly what we were hoping to get. And so we're done. There are no non-permissible values in this proof because sine has no denominator, right? There are no possibilities of having denominators of 0, and so we have no NPVs. And so that's it. Hope this helps. Thanks for watching.